Welcome to Hot Chips 32. Session 3, Edge Computing and Sensing.
Hi, it's Krista here from UC Berkeley and Sci-Fi, and I'll be the session chair for this next session. So we have three great talks, and the topic of this session is edge computing and sensing. So looking at some devices out on the edge. So for the first talk in the session, we have the Shanti 910, which is Innovating Cloud and Edge Computing by RISC-V. The talk will be given by Yu Pu, who received his PhD degree in electrical engineering in 2009 from Eindhoven University of Technology in the Netherlands. He's now with Alibaba's Computing Technology Lab, and he leads R&D in lower power SoCs for edge computing at scale to facilitate cloud-to-edge and edge-to-edge infrastructure. So I guess we can start the talk now.
Everyone, welcome to my presentation. My name is Yu Pu. I'm from the T-Head division of Alibaba Cloud. With my greatest pleasure, I will present the topic Shanti 910, Innovating Cloud and Edge Computing by RISC-V. The story is about using RISC-V to facilitate Alibaba's end-to-end and cloud-to-edge computing infrastructure. Here, the codename Shanti refers to a heavy sword made from dark iron in Chinese tales. Although the evolving RISC-V architecture is not yet mature enough in terms of technology and ecosystem, we believe it has great potential. The intention of this work is to contribute to the high-end, high-performance embedded computing cores based on RISC-V through open-source collaboration. This work is from the T-Head semiconductor or the Pinto Ge semiconductor. For many of you who may not have heard about the T-Head, it is a relatively young organization in Alibaba, which is the business entity of the Alibaba Group, specializing in the integrated circuit design with the primary goal of developing the next generation chips for cloud, data centers, and embedded IoT chip products. We have very strong commitment to open source. In Alibaba Cloud, there are many teams that are involved in this work, all the way from the hardware team, firmware team, software team, and system team. The digital economy is becoming an unstoppable force. Alibaba, as an internet company, we are dealing with the exponentially increased global data. This chart shows the predicted data volume, which hits 175 zettabytes by the year of 2025. Zeta is the metric system that denotes the multiplication by 10 to the power of 21. Now, whether we would really be lagging at such a scale is another question. The key concern is the underlying computing power that is to sustain such an astronomical data traffic. The AIoT is largely fueling the wave of research and development of low power and cost-effective chip infrastructure. RISC-V is very attractive at this point in time because, as an alternative to closed and costly ISAs, the open and free ISA of RISC-V accelerates processor innovation through open standard collaboration. The scalability, extensibility, and modularity enable processor customization and optimization for domain-specific workloads, such as machine learning accelerators, network processing, security enclave, storage controllers, and so on, thereby largely boosting processing efficiency and reducing design costs. RISC-V is also very easy to accompany with other domain-specific IPs from partners, both from technical angles and business perspective. RISC-V is nowadays becoming a mainline platform in Unix and Linux operating system. It is also fully supported by our Ali OS. As the toolchain is getting more and more mature, it further improves software experience and drives down software development costs. As said, Xuantie is T-Head's RISC-V series of processors. The intention of Xuantie series is not to compete with any non-RISC-V cores on the market, but rather contribute to the open-source RISC-V community. The work in this talk centers around the Xuantie 910, which is the high-end 64-bit RISC-V architecture with AI vector engine. In terms of performance, it is very similar to Arm A73. At the other performance spectrum end, our smallest offering in the series is the Xuantie 902 with hardware TEE, a trusted execution environment. It is in the microcontroller class, which is similar to the Arm Cortex-M0+. From the Xuantie 902 to Xuantie 910, in progress, there are multiple variants with different embedded performance and power levels, namely Xuantie 903, 905, 907, and 908. In this slide, we show the diagram of the Xuantie 910 multi-core cluster. Xuantie 910 is fully in compliance with the RISC-V RV64 GCV instruction set. The RV64 GCV designation means that Xuantie has implemented the base 64-bit RISC-V ISA. On top of that, it enables the compact 16-bit wide instructions as well as the regular 32-bit wide instructions. It also has the vector instructions, although the standard body itself is still in development. Xuantie 910 exploits a homogeneous multi-cluster architecture. A cluster is composed of up to 4 cores capable of booting Linux operating system. Each core supports a 32 or 64 kilobytes of L1 instruction cache and a 32 or 64 kilobytes of data cache. Each cluster has a shared inclusive L2 cache memory. Each single core utilizes the state-of-the-art 12-stage deep pipeline out-of-order multi-issue architecture. The instruction fetch unit uses a high-performance hybrid predictor, which makes predictions of branch direction, branch address, function return address, and indirect jump address. The instruction decoding unit can decode 3 instructions simultaneously. The out-of-order issue engine can issue up to 8 instructions. Most importantly, Xuantie 910 is one of the first commercial processors that adopt the RISC-V vector extension proposal. The vector engine significantly boosts the performance of vector processing, especially for AI and machine learning applications. A series of industrial benchmarks for embedded CPUs have been performed to evaluate the performance. One of the benchmarks is the core mark. Note that such benchmark is only for core performance evaluation, as it is basically all cache hit and it is hardly affected by the DDR latency. In this figure, the performance is compared with various of embedded processors. The Xuantie 910 processor reaches 7.1 core mark per megahertz, which is by far the highest performance RISC-V processor available on market. By the time writing the article, we saw the news about the upcoming Sci5U84 processor, but because there are no official data, we cannot make fair comparison without knowing the evaluation conditions, the hardware configuration, and the software compilation toolchain details, but we would be very happy to include it as a new reference point once its information becomes available. As shown in this table, beyond the RISC-V RV64 GCV support, the Xuantie 910 supports the standard user, supervisor, and machine privilege modes. Xuantie 910 includes a standard 8/16 region PMP physical memory protection and a SV39MMU, which is compatible with the RISC-V Linux specification. It also incorporates standard Clint and PLIC multi-core interrupt controllers, timers, and debuggers. It has performance monitors and I/O slave interfaces. The LSU supports unaligned memory data access. The vector extension is in compliance with the RISC-V 0.7.1 proposal, supporting computation in the format of FP16, 32, 64, and integer 8, integer 16, 32, and 64-bit. To improve the performance, 20 features RISC-V vector extension and a series of non-standard custom extensions, including extensions to arithmetic, bit manipulation, load and store, TLB and cache operations, and multi-core synchronization. In addition, there are extensions for the MMU to support page-based memory attribute management and for the interrupt controller to support permission control. All the extensions are supported by our compilation toolchains. Through hardware configurations, the non-standard extensions can be disabled, allowing 20 to operate in a mode fully compatible with the standard RISC-V. Compared with the native RISC-V ISA and compiler, the performance of 20 with instruction extensions and optimized compilation has been improved by about 20% when using different industrial benchmarks. The pipeline of the 20 core is shown in this slide. The front end of the pipeline consists of 7 stages. The instruction fetch unit can fetch 8 instructions per cycle. The instruction decoding unit can decode 3 instructions simultaneously per cycle and can rename up to 4 instructions using physical registers. The out-of-order issue engine can issue up to 8 instructions per cycle. The backend of the pipeline features out-of-order memory access, dedicated branch processing, and out-of-order vector computing. It has multiple execution units, including 2 single-cycle ALUs, 1 single-cycle branch jump unit, 1 dual-issue out-of-order load and store unit, 2 scalar floating point units, and 2 vector execution units. Because of the 128-bit instruction fetch unit, which contains a maximum of 8 instructions, it is highly likely that the instructions have some branch instructions inside. The 20 uses the hybrid multimode branch prediction to predict the directions and target addresses of branches, including absolute branch, conditional branch, indirect branch, and function call return address. This allows program jumps to be initiated as early as possible, reducing pipeline bubbles caused by program flow changes. All instructions prefetched through branch predictions are cached in the instruction buffer. When the branch prediction is correct, the instruction buffer content is accumulated. Therefore, even when cache miss occurs, the instruction fetch unit can still provide sufficient instructions to the subsequent instruction decoding unit in the pipeline. To facilitate instruction fetch for small loops in programs, the instruction fetch unit also has a loop buffer where small loop bodies can be entirely buffered. The 20 RISC-V processor supports dual-issue out-of-order load store unit. The LSU can process 1 load instruction and 1 store instruction in parallel. The dual-issue LSU requires dedicated load pipe and store pipe. It also supports speculation failure prediction. 20 enables fast load and store completion. It takes 3 cycles for load to use and 1 cycle store execution. For high-performance applications, there exists a large gap between the memory access bandwidth and the processor running speed. Although multi-level cache can dwarf the impact of memory war, there are still many scenarios where either data is used very few times or the cache capacity is simply not sufficient. The 20 provides a unique multi-mode and multi-stream data prefetch approach to enhance the data prefetch capability. By pattern matching the data streams, 20 effectively prefetches data and backfills the L1 or the L2 cache and reduces the probability of store caused by high memory latency. In addition, it supports virtual address cross-page prefetch. When data is prefetched at the page boundary, a conversion for the next virtual page is automatically requested. Once the physical page address is obtained, data prefetch resumes. The Xuantian adopts the SMP multi-core architecture. Up to 4 cores are grouped into one CPU cluster, and up to 4 CPU clusters are connected using N-core. The cores are connected through an internal bus with coherence protocol. Each core has decoupled processor interface unit. The cores share an inclusive L2 cache memory with a maximum configurable size of 8 megabytes. The L2 cache supports MOESI coherence protocol, a snoop filter that monitors access by the cores to the shared L2 cache effectively reduces the inter-core communications. The Xuantian is one of the first commercial processors that adopt the RISC-V vector extension proposal. Compared with the traditional fixed-length SIMD instruction sets, such as Arm Neo, Intel SSE AVX, the variable-length vector instruction sets, such as Arm SVE and RISC-V vector extension, not only provide more flexible parameter selection for hardware, but also enhances the portability of upper-layer software across different hardware platforms. Based on the 0.7.1 RISC-V stable release, the Xuantian supports the execution of dual-issue out-of-order vector operating instructions. Each vector pipeline supports floating point 16, 32, 64, and integer 8, 16, 32, and 64 operations. To balance the bit-width ratio of arithmetic logic operation to the memory load and store access, 2 vector pipes with 128-bit V length each have been implemented. With such configuration, Xuantian can generate a total of 256-bit operation results in one clock cycle and complete a 128-bit vector load and store operation. It directly accesses the L1 cache on each vector load and vector store. Overall, the vector engine delivers over 300 gigaflops of FP16 computing power per CPU cluster. When widening to FP32, the computing power becomes half. This figure shows that, along with the hardware, we also released a comprehensive integrated development environment for Xuantian, which is an IDE that enables RISC-V graphical trace, profiling, and instruction-accurate simulator with JTAG Online debug. GNU's combination tool collection is also fully supported. A snapshot of the profiling tool is shown here. The compiler of Xuantian has been co-optimized along with the hardware architecture to support custom instructions as well as dead store elimination optimization. Because there are hardly benchmarking results available from high-performance RISC-V processors of this kind, we use the Arm Cortex-A73 as our reference. As high-performance embedded processors, the Arm Cortex-A73 and our Xuantian have many architectural similarities. For example, the deep pipeline stages, the instruction issue width, and so on. This allows us to better analyze and compare the pros and cons of RISC-V and ARM at the ISA level. The experimental Cortex-A73 processor is from the Huawei Kirin 970. It has 64 kilobytes L1 instruction cache, 64 kilobytes L1 data cache, and 2 megabytes of L2 cache memory shared by the instruction and the data. For a fair comparison, the Xuantian is configured for the same L1 and L2 cache sizes, and it uses the GCC 8.1 compilation toolchain. The figure shows the performance of the EEMBC benchmark, which is a benchmark for the hardware and software used in autonomous driving, the Internet of Things, mobile devices, and other applications. Similarly, we evaluated the MBench, which is a performance testing framework for .NET applications. Overall, the performance of 玄铁910 is on par with the Arm Cortex-A73. We want to claim that the benchmarking results are by no means suggesting our 玄铁910 is up to the perfection of the Arm flagship Cortex-A73 core. In fact, 玄铁910 has just made its debut. A multi-year open collaboration is needed from the RISC-V community to cover numerous corner cases. Here shows an image captured from a demo of 玄铁910 core. The demo is obtained from FPGA. It runs an image recognition demo. As can be seen from the system booting information, the CPU subsystem targets a 2-core single cluster. Each core uses 64 kilobytes of instruction cache memory and 64 kilobytes of data memory. The 2 cores share 2 megabytes of L2 cache memory. The cores have vector engines and the vector length is 128. The MMU has 1024 joint TLBs. In this slide, the left figure shows the exemplar floor plan of a dual-core cluster. The performance from post-layout simulation is summarized in the table next to the figure. In a TSMC 12nm FinFET process technology, the implemented silicon areas are 0.8 mm square and 0.6 mm squares, respectively, for a single core with and without the vector execution unit, excluding the L2 cache memory. When operating at 0.8 volt power supply, the core reaches over 2 GHz frequency using LVT standard cell library and ULVT SRAMs. If we could use ULVT standard cells and operate at 1.0 volt power supply voltage, which is the voltage boosting mode, a 2.5 GHz main frequency can be achieved. In another experiment with the 7nm FinFET technology, the main frequency of a single core can reach up to 2.8 GHz. Since the official launch in July 2019, the FPGA implementation of 玄铁910 has been already deployed in the data centers of Alibaba Cloud, mainly for application-specific acceleration. One of such applications is the blockchain transaction used by our Ant Finance business unit. The implementation of the Cynix VU9P FPGA runs at about 200 MHz frequency in Linux operating system. Taking blockchain transaction acceleration as an example, in terms of per-core performance, thanks to the custom extensions, the FPGA edition is still 20% higher than the x86 64-bit Intel Xeon Platinum 8163 CPU that runs at 2.5 GHz in Ubuntu operating system. Besides the FPGA deployment, the ASIC edition has been taped out in Q1 2020. One silicon in the 28 HPC Plus process technology has recently been back. At 1 volt power supply voltage, the frequency can achieve 1.6 GHz for 玄铁910 core with vector engine. The measured power is about 0.3 milliwatts per megahertz. The achieved benchmark score is 7.1 for Cormac and 5.8 for Drystone. We also have a 12nm FinFET edition ASIC silicon in pipe, which will be back for bring up. We will be happily sharing the results later. In addition to internal usage, Alibaba also promoted the 玄铁910 to facilitate external customers for edge computing applications such as edge servers, industrial control, and ADAS based on the SoC platform called Wujian. Wujian, in many ways, is a platform developed for agile SoC design. Wujian is an all-in-one chip design platform that provides an integrated solution to chip architecture equipped with basic software, algorithm, and the development tools. It is composed of many modules such as the SoC architecture, processors, various IPs, interconnects, operating systems, software drivers, and the EDA tools. The Wujian platform undertakes about 80% of the general design workloads for an AIoT chip, allowing the chip-related R&D enterprises to really focus on just figuring out that remaining 20% of the dedicated but highly differentiated design work, reducing the R&D threshold of the SoC design while also improving the R&D efficiency and the chip quality. In other words, the Wujian platform makes the customization of AIoT chips a lot easier than before. It helps the chip design companies reduce the cost by 50% and shrink the design cycle by 50%. To summarize, the Xuantian 910 is a high-performance, 64-bit embedded multi-core RISC-V superscalar processor. It is fully based on the RV64 GCV instruction set and features custom turbo extensions. It also has an AI vector acceleration engine. The tool chain of Xuantian 910 also has been largely optimized to fully support the custom extensions. By hardware and software co-design, to date, Xuantian 910 delivers very good performance for a number of industrial computing benchmarks. With that, let me conclude my talk. Thank you very much.
In that case, I mean, when he's talking, it should.
Thank you for the talk. Came up on the Slack channels. A few of them were answered in the talk, but let me try and pick out
that's good.
The ones here. So Cliff Young asks, what edge applications are you using the Shanti for? Is it deployed as a standalone CPU chip, or is the core intended to be integrated into SoCs?
That sounds good. Yes, I have a headset here.
Hi, let me just repeat that question. So the question was, what edge applications is this being used for? Is it intended to be deployed as a standalone CPU chip, or is the core IP intended to be integrated into other SoCs? This is from Cliff Young. Sorry, you want me to repeat the question?
I cannot hear you.
Yeah, I just don't hear anything after I. Yeah, the question was, what edge applications is this being used for? Is it deployed as a standalone chip, or is it intended to be a core IP that's integrated into other SoCs?
Yes. So it's basically being integrated into SoCs together with some other like lightweight GPUs, MPUs, and other LPDDR, GPIOs, things like that. It's going to be like high-end embedded cores for SoCs. Yes.
Okay, thanks. Another question, people asking, will we be able to get the source code? Is this open source?
Oh yeah, that's actually a very good question. And thanks Hot Chips, thanks everybody for the interest in this work. Actually, we are actively working on the open source procedures. I came to know that actually to open source a high-end core is not that straightforward because there are going to be some legal approvals. We are going through that. We are also talking with multiple reputed, open source organizations, figuring out what would be the best channels to open source the codes. And we are also thinking ahead of time, once it's being open sourced, so how to best manage the repositories and update and maintain all users worldwide. So yes, we are working on that, and yeah, once it's available, we will release it. Yes.
Okay, great. Another question. Do you have plans to support the vector version 1.0 specification? That's from me and a few other people.
Yeah, I mean, so currently we are on the 0.7.1. When we designed the chip, it was still at that standard, but we are actively following the standard evolution, and we are working on that. Yes.
Great, thanks. Maybe just one question to end up here. When you fetch 8 instructions per cycle, what's the average number that are useful before a branch? Do you have some hardware or software optimization to align the blocks, or is do 8 instruction boundaries an optimization?
Yeah,
I guess the question is about aligned.
Yeah, that's actually a very good question. And my experience was that this is highly dependent on the application itself, and also depends on your configurable, the L1, L2 caches, the memory sizes, and the way how you prefetches. So it's actually very difficult to say what's the average consumption of the instructions. So that's why we don't have the number there. But we would be happy to to discuss, or like to do some experiments if we have some suggestions.
Great, thanks for a great talk. The Slack channels remain open for people to hopefully be able to answer some of the questions. But at this point, we'd like to move on to the next talk. So thank you very much.
Thank you, thank you, everyone.
So please applaud on the Slack channel using the applause thread. So the next talk in this session is called a technical overview of the Arm Cortex-M55 and Ethos-U55 ARM-capable processors for endpoint AI. So we have 2 speakers to be giving the talk live. We have Allan Skillman, who is a distinguished engineer at Arm's Central Engineering CPU Group based in Cambridge, UK. And he is the technical lead for the Cortex-M55 microcontroller. And he's previously worked in several generations of energy-efficient embedded processors. Allan has a PhD in high-energy particle physics. Before working at Arm, he worked at University College London and CERN in Geneva. The second speaker is Tomas Edso. He's a senior principal engineer at Arm, and he's the hardware tech lead for the Ethos-U55 micro NPU in the Arm machine learning group. Tomas joined Arm Sweden in 2008 as one of the founding members of the video IP company Logipad. He has a master's degree in engineering physics from the University of London. So I look forward to the presentation.
Let's see. Hopefully you can see me. So thank you very much for that introduction. As I said, we're here to talk about the ARM solution for endpoint AI, which is made up of a processor, Cortex-M55. It's our latest mid-range M-profile processor with helium technology, which I'll talk about in a minute, and Ethos-U55, which is a neural processing unit, a micro neural processing unit designed to accelerate machine learning inference in an energy-constrained embedded for IoT devices specifically. So can we move on to the next slide? Okay, so if we look at a typical IoT device today, everyone's familiar with a smart speaker. So this is a device that's in everybody's home, and it's all about IoT technology with the endpoint AI capability, particularly for keyword spotting. Everyone's familiar with talking Alexa or Hey Siri or OK Google. And really what the idea here is that you do as much processing locally for efficiency and to some extent for security, and then leave the heavy lifting to the cloud. So typically we're looking to do some DSP on the front end for microphone beamforming, and to do some some feature spotting, and then feed it onto a back end that does machine learning to pull out the keywords, usually using a precompiled model. So it's really just inference. Anything more than that is pushed upstream. Now, generally speaking, there's too much work here to do for a single processor alone. Now, there's a couple of solutions you can go in for that. Either you could go for a high-performance general processor. That's really potentially wasteful for power and area if you have to run it all the while, when really you want to be running as low power as possible to do the weighting for input from the user in the room. Another alternative is to go with some sort of multi-core solution, so potentially multiple MCUs, or even using a more traditional DSP processor to do the front end, and then maybe an MCU to do the back end machine learning. Now, this is efficient, but it's complex in terms of software, and it has a more complex ecosystem. So the ARM approach here is to actually use the mixture of an energy efficiency MCU with enhanced compute capabilities to do both the DSP and the basic machine learning, and then scale this solution with the potential for an NPU accelerator to do some heavy lifting, potentially not even to need to go to the cloud, so in enhanced efficiency and better security. Can we move on to the next slide, please? So, in terms of our approach, it's all about energy efficiency. So it's all about balancing the amount of work done over the power consumed to do that work. Now, there's several approaches you can go here. We could go to a traditional VLIW machine, but it's not really the ARM way. And also, it has the same sort of issues that solutions have today. It requires multiple software tool chains, very specific programming capabilities and skill sets, and it needs some specialist hardware as well somewhere as well. Now, we could go to a superscalar solution. So we could get our performance by actually running a lot more instructions per cycle. Now, we do that sometimes for general purpose compute, but it will give us a lot of extra control capabilities as well as a DSP, but it would be relatively wasteful in the environments we're doing, where actually the amount of control we need isn't that much, but we need more compute. And if we were looking at the regular ARM ISA, then we would be looking at the data types that are available are not particularly useful. They're very limited. We have a narrow data path of 32 bits, and we usually only support some types of data types. So away from that, SIMD looks promising. We do have SIMD capability in our regular ARM cores, and we have solutions in the high performance compute areas in our what we call our application processors or A profile processors. And you may well be familiar with our solution called Neon there. Now that's very close, but it's not quite a good enough fit. Now, the reason it's not a good enough fit is that we really need a couple of features within an embedded type space. One is determinism. We need to be able to understand how long something's going to take. And we also need low interrupt latency. So we need the ability to know we can take an event because we have a very event-rich type of software environment. And of course, we need low power and we need low area. And these, of course, are the most efficient, most important things for heading for efficiency. So have the next slide, please. So the solution we have is what we call Helium technology. So Helium is part of the ARM v8.1M architecture. That was announced last year. And this is the new version of the ARM v8M architecture that was used. The original one was used in the Cortex-M33, which is a very well-known M-profile processor on the market today. And Helium is all based around energy-efficient compute. So it's a vector-based architecture, and it's based on 128-bit fixed vectors, but it reuses a lot of the resource that's available in the regular ARM architecture today. In fact, it maps onto what we call the extended register bank, which is traditionally used for floating point, and also uses the regular register set together in the same instructions. So it has a really compact footprint. So it's also very versatile in data types. It can support 8-bit data, integer, 16-bit data, integer, 32-bit data, in integer as well as 16 and 32-bit floating point. Now, Cortex-M55 is the first implementation of and uses this Arm v8.1 architecture, and that's available for general license now. It's highly configurable. You can take it from a very simple microcontroller all the way up to a very capable full compute processor. So depending on what sort of area against the functionality you need. It has a compute-focused memory system, which I'll talk about in a minute, and it's very feature-rich. So over and above the Helium technology, it also contains our trust zone solution for security. It has double precision scalar floating point. That's a new feature in this space. It has advanced power control capabilities, very important in embedded integration. And it has new debug capabilities, including has performance monitor unit, which is taken over from some of the A&R profile devices we have, and also has optional functional safety capabilities with some embedded applications where that's very important. We also have support for accelerator capabilities. One is the coprocessor interface, which we have supported previously on the Cortex-M33, but also support for ARM custom instructions in the next version coming in 2021, which is very exciting. So we move on to the next slide, please. So the Helium architecture. So this is a vector architecture based on beat-based architecture. So Helium is all about the balance between performance and power, so to maximize energy efficiency. So we have a beat-based architecture, and each beat is 32 bits of data, which means in any beat we can have either 4 8-bit, 2 16-bit, or 1 32-bit operation. But there are various different variants of the beat architecture, which we can go all the way from doing just 1 beat per cycle up to 4 beats per cycle, filling in a whole 128 bits. Cortex-M55 sits in the middle in a very nice slot for energy efficiency and runs 2 beats per cycle. So a 64-bit data path. So it is both a good balance between good throughput, but also not using excessive amounts of resource or excessive amounts of power to be able to operate each cycle. Now, over and above that, one of the features of the Helium technology, which gives it its unique capabilities, is the ability to overlap these beats. So essentially, we have different structures within the processor that are not necessarily being used at the same time on the same data. This allows us to overlap one type of operation onto another type of operation, so that when we're operating on one set of 64 bits of data, we can actually move or operate in parallel with other half of the vector. So the example here, you can see the very simple but actually very, very important sequence of doing a load followed by a MAC followed by a load followed by a MAC. You can see, because we can overlap the load with the MAC here, we can actually operate at maximum throughput, essentially feeding a MAC with 64 bits every cycle. We have the next slide, please. So of course, if you can compute 64 bits a cycle, it's very, very important to be able to feed that compute as well. So Cortex-M55 has an advanced memory system. It's actually broken up into 2 areas. So we have one part of the memory system which is dedicated to low latency, highly deterministic capabilities based on what we call a tightly coupled memory system, usually connected to close coupled SRAM. That gives single cycle performance and very deterministic behavior. But of course, not all the data can fit into an SRAM on the device. And a lot of the types of data is involved in, for example, machine learning, like the weights are actually large sets of data that are better stored on an off-chip, potentially even in DRAM. Now, in order to support that, we also include a full standard Harvard cache system and an AXI interface that can efficiently bring data into the processor in large amounts from a large external source. So we support all the capabilities of a DSP, but using regular types of memory. In fact, if we move to the next slide, you can see that although Helium technology is a regular ARM technology and uses a regular instruction set architecture, we support the same sort of features of DSP through either generic mechanisms or very similar mechanisms. So for example, we support the equivalent of zero overhead loops, effective loop unrolling in hardware. We can support complex numbers within our vectors, and we can support a number of memory manipulation techniques like circular buffer, bit reverse addressing, by being able to manipulate data based on a vector itself. It's what we call scatter-gather memory, essentially the ability to compute addresses based on the vectors themselves. So you construct, for example, a circular buffer through a set of addresses within a vector. Can we move on to the next slide, please? So let's look at some of the performance here. So what this graph is showing is a comparison of the Cortex-M55 against some of our other Cortex-M processors, all set at ISO frequency and relative to a Cortex-M4, which is a very, very familiar, very popular Cortex-M processor from ARM. Now, this is based on a set of DSP and machine learning-like kernels, so small microkernels that are based off the SimSys software library, essentially breaking down to machine learning and DSP type capabilities. There's fast Fourier transforms in there and other types of filters, data transfer, statistical type algorithms. And what you can see here is if you compare to our other Cortex-M processors, the Cortex-M55 is significantly better performing in terms of instructions per cycle, particularly if you look at the 8-bit fixed data type and the 16-bit float type, because these operations, both in hard precision floating point and 8-bit data, have not really been available in our processors before, and not at all in terms of vector processing. So we move on again, please. So that was simple algorithms, but let's have a look at something a little bit more complex. So what we have here is a keyword spotting algorithm. So this was something that was developed by ARM. It's a completely open algorithm. You can see the links at the bottom, both to the software on GitHub, but also the paper. It's a very interesting paper. It was developed by our colleagues in San Jose. Now, this is a completely generic algorithm. It supports a lot of different types of neural net, but also includes the front-end DSP to do the feature extraction. So running this algorithm is actually a really good real-world example of showing what we can actually do within the Helium technology, and to compare it with our other processors. So if you look on the right-hand side of this slide, you can see a comparison across, again, the other Cortex processors, Cortex-M4, Cortex-M33, and Cortex-M7, and you can see that Cortex-M55 is significantly higher performance in terms of a full algorithm of keyword spotting. So it's significantly more energy efficient, and obviously that gives it the ability to either run at lower frequencies or being able to be optimized to make it lower energy, but still perform the same task. Okay, can you move the next slide, please? So of course, keyword spotting is just one application. There are lots of other endpoint AI applications, and they require different types of performance capabilities. So if you look on the left-hand side here, we have vibration detection and sensor fusion, as well as keyword detection. Now, these are things that I said earlier can be done on regular processors, although we tend to be getting to the end of their performance capabilities. And this is where Cortex-M55's vector capabilities with Helium gives it an extra more room in order to stretch out. So you can see you can go from keyword detection to anomaly detection. This is very similar, but maybe used in industrial environments, looking for issues with machinery, or we're even in a home environment, looking for maybe in glass breaking or some other thing happening within the house. And we can even do a little bit of object detection. But generally, as we move upwards, we'll need more compute capabilities. And that's where some of our neural processing unit comes in. And you can see you can move all the way through some of the more embedded technologies and applications by using Ethos-U55 with Cortex-M55. And then if you really need to, high-end MPUs can be used at the top end to get the maximum number of operations per second. So I think this is a good time to hand over to my colleague in the machine learning group in Lund, Sweden, Tomas Edso. So Tomas? Are you there, Tomas?
No. Okay, so am I live now? Okay, so I think I'm not seeing the same slide as maybe it's delayed a bit, but okay. So I'm happy to speak here for ARM, and I'm happy to present about the Ethos-U55, which is the micro MPU that was launched at the same time as the Cortex-M55, and they're both designed together specifically for AI applications on constrained embedded systems. So the Ethos-U55 is designed to work alongside an M-class CPU. We believe that the most efficient for overall all AI performance would be the M55 that we just heard about. But in fact, it works alongside other Cortex-Ms as well, so, such as Cortex M7, M33, and M4. And in the slide that I hope we're seeing right now, we see an Ethos-U55 overview where you see the Ethos-U55 on the right. And then the type of system it is designed for is a typical embedded system where you have a fairly large system SRAM with a good connection, a fast connection, and then you have some system flash, typically a lot slower, that we assume are memory mapped to the Ethos-U55 and Cortex-M55. The Ethos-U55 works as a companion and handles all the neural network models, completely offloading the Cortex-M CPU for most popular networks. It both CNNs and RNNs. One thing that makes it good, well suited, and that it has been designed for is low bandwidth. So that's why we have efficient weight compression, which allows the models stored in flash to be compressed, and that improves both performance and power consumption. The model needs to be quantized 8 or 16 bits. So Ethos-U55 is also configurable, and the main configuration knob is the number of max per cycle, which can be configured to 32, 64, 128, and 256 max per cycle. And that gives a range of something like tens of GOPS to half a top or top, depending on your implementation target. And then I would like, next slide, please. This slide is showing the typical data flow of the Ethos-U55. Should be slide 12. This is a quite low level how the M55 and the Ethos-U55 work together. So it's assumed at the start of an inference job, you have pre-compiled your model and put it into system flash. And an application on the Cortex-M puts the input activations into a buffer in SRAM. Then the host will start. The Ethos-U55. I think you can probably go. I can't see the arrows on the presentation that's live now. There should be arrows as well, if that might be an update to the slide. The host starts the Ethos-U55 by writing locations to where the model is stored and where the activations are stored. Pretty much just setting up a few registers over an APB interface. Then the Ethos-U55 will start automatically when the pointers are set up, and then it runs the whole inference job automatically by reading the pre-compiled command stream from Flash and using the SRAM buffer as a scratch buffer. And the results at the end of the inference is written back to the system SRAM memory. And at the end of the inference job, Ethos-U55 will signal the Cortex-M with a single interrupt stating that the job has been done. So next slide, please. This is the slide should be showing the Ethos-U55 interfaces. And it's quite a simple set of interfaces. You have a single clock. You have the APB interface, a 32-bit APB interface, which is used for the setting up of the Ethos-U55, typically very low bandwidth at the beginning of the inference, just a few pointers. Then we have the two AXI interfaces. They're used. One is a read-only, which is there so you can map your flash traffic onto that, and for the weights and pre-compiled command stream. And then the second AXI interface is used for read and write to the SRAM. And the reason we have two is to separate the slow traffic from the fast traffic and making it possible to have an efficient interconnect running these. Then there is a power and a clock Q channel interface. And worth mentioning here is that the power up and down of Ethos-U is very fast, in the order of a few hundred cycles. So typically, once a job is done, you automatically power down the Ethos-U55, as there is no state remaining inside the Ethos-U55 after an inference. So typically, there is no power consumption between inferences. Next slide, please. This slide is for should be the network supports in Ethos-U55. Slide 14. Network supports. So the Ethos-U55 is supporting a fixed set of operators. Yes, the Ethos-U55 supports a fixed set of operators and execute any network that okay, so this networks that map completely are, for example, RESNext50, WAV to letter, but also actually, since this slide was done, we have added support also for the softmax operator, so it's not actually up to date, this slide. So all the mobile nets, deep speech, and a lot of other networks also map completely to the Ethos-U55. But there are instances where an operator is not supported by the SIMSYS, by the Ethos-U55, and what is then done is that that operator will fall back to software which may be optimized through the open source CMSIS NN library, and then fall back to the Cortex-M. Next slide, please. So this is the Ethos-U55 optimized software flow. In the first generation, the Ethos-U55 is based on the TensorFlow Lite microflow. This is something we are rolling out with. We are looking in the future to other frameworks as well. But for now, this is the chosen framework. So what you do is you train your TensorFlow Lite model in the TensorFlow framework. You quantize it to 8 or 16-bit. By using clustering and pruning and other techniques, you can prepare a model that then is suitable for compression. Now you can take that TensorFlow Lite file and run it on your target device. And if you do that, it will run as normally on your Cortex-M CPU. You can make it fall back to CIMS, SNN, and that will run your inference. But what we've added is the neural network optimizer tool, which is an open source tool, which if you run your TensorFlow Lite flat file through that tool before you run it on your target, that tool will optimize for your Ethos-U55 by identifying pieces of the graph, or in many cases the full graph, and optimize and schedule it and make it possible to run it on the Ethos-U55. If there are any layers that the optimizer notice is not supported, it just leaves that operator inside the TensorFlow Lite file, and that will then fall back to CIMS, NN if available, or reference kernels if that is a completely unoptimized operator. And this flow, we believe, is a very flexible and future-proof way of supporting and using the Ethos-U55 and M-class in an efficient manner together with popular frameworks. Next slide. So as an example use case, we have looked at just for the combination of M55 and U55, we have looked at full use cases. And a popular one is a smart speaker, where you initially have some pre-processing of your signal and then passing it onto networks for detection of various kinds. And in this slide, it can be shown that there are two modes of operation. One low power mode, where the Cortex-M55 runs alone with noise cancellation and voice activation detection or activity detection. And then once in this mode, it can run on a reduced clock speed for low power. Once detected, it can wake up and do full noise cancellation and beamforming on the M55. And you can do the keyword spotting on the M55 if you wish. It could actually be done on Ethos-U55 as well, since that's a neural network load. But what is possible with Ethos-U55 is to run full speech recognition, something that would otherwise be too heavy for the M55. And then the M55 can again run audio playback for the response at the end. And in this higher mode, you can have a full speed of the M55. This is an example we've been looking at. And next slide, we have some results. So if you look at running such a use case only in a Cortex-M7 and just then moving it to the M55, you will see a 6-time uplift. Having the M55 plus the U55 will give you a full 50-time improvement. And that is for the full use case. Something we believe might be more interesting than just the neural network part, which when running on the Ethos-U55 is obviously much larger than 50 times. The full use case is having an energy efficiency boost of up to 25 times when running on the Cortex-M55 Ethos-U55 combination as compared to a Cortex-M7. And this would obviously lead to a much faster response. You can make smaller form factor products, or you can use this additional power for improved accuracy in your voice assistant. Next slide. Yes, next slide, please. Yeah, so the last is summary. So in summary, we believe that our Cortex-M55 and U55 is the ideal combination for a full AI solution in embedded system. They're both designed together for low power and for security together, and also have the configurability to tune to your target application. And the role of the Ethos-U55 is to give a high performance and low power on neural network models, whilst reducing the system cost of the flash and memory size by advanced offline compiler scheduling and model compression. And then the Cortex-M DSP is used for the pre and post processing, also in the low power envelope. And the combination also allows this to work with, backward software compatibility with older M-class models and familiar, easy to use software and tooling frameworks. So thanks a lot for that. And we can go back to the moderator.
Hi, thanks for the presentation. We are a bit over time, so we won't be doing any questions live, but the folks from Arm have been active on the Slack channel answering questions, and I think they'll continue with that. So please refer to the Slack channel for this talk to get more questions answered. Okay, thanks for the presentation. So the last talk in the session is called PGMA, Scalable Bayesian Inference Accelerator for Unsupervised Learning. The speaker is Glenn Coe. He's a postdoc fellow at Harvard University, working with Professor Guillaume Wei and Professor Dave Brooks. Before joining Harvard, he got his PhD at Illinois. Before that, he was with Samsung, working on R&D of XNOS processors for smartphones. So looking forward to the talk. So please take it away, Glenn.
Hello, everyone. It is my pleasure to be here at Hot Chips. My name is Glenn Coe. I'm a postdoctoral fellow at Harvard University and the CEO of Stochastic. Today, I'm going to present our work on a scalable Bayesian inference accelerator for unsupervised learning. For those of you who are not familiar with Bayesian inference or unsupervised learning, I'm going to briefly talk about what they are in the beginning of my talk, and perhaps throughout this, through this opportunity, I'm hoping to get more of you interested in this exciting class of machine learning algorithms that have not been readily studied by the hardware community. So with that, I would like to start out by the fundamental problem which I believe all machine learning implementations are trying to target, which is the exponential data growth problem. Humans are generating data at an exponentially increasing rate. And recent advancement of machine learning have allowed us to extract useful information from data without much human intervention. Or our goal is to try to reduce the human intervention, but I believe that we still haven't fully accomplished that yet, because if you look at a typical data scientist, 80% of the time of a typical data scientist is spent on sourcing and cleaning data. And furthermore, deep learning requires very large labeled data sets, which has spun off an industry of its own, where there are companies that are focused on data annotation services. So there are multiple ways of improving this problem or solving this problem. And we believe that one approach would be to look at how we can use less data, not more, to train AI. If we look at humans need a lot less data than machines to generalize about and draw conclusions. For example, babies can learn by crawling around and playing with toys or simply observing the behavior of adults. And one research from neuroscience shows that human brains actually may be learning through a combination of multiple learning mechanisms, including unsupervised learning, reinforcement learning, and supervised learning. And out of these learning mechanisms, today I'm going to focus a bit more on the unsupervised learning, or the semi-supervised learning, which allows us to extract information without any kind of supervision or a labeled data set. So one class of machine learning algorithm that may be used for this type of learning is called probabilistic learning, or often called Bayesian learning, where the probability is used to represent uncertainty about the relationship being learned. And it describes our beliefs about the true relationship that are expressed in probability distributions. And for learning and predictions, we use what we call Bayesian inference, which updates one's beliefs upon observing the data using Bayes' theorem, which is shown on the bottom of the slide. So on the right, you can see that some beliefs about the relationship can be described in likelihood or prior distribution. And then upon observing the data, we could use Bayes' theorem to update our beliefs, which would in result update the posterior distribution. And this process of doing using Bayes' theorem is again called the Bayesian inference. And this probabilistic learning or Bayesian learning is known to be more powerful for online learning, where you're learning from small chunks of scarcely or unlabeled data. An example would be COVID-19 predictions, where we have limited understanding of the problem itself, and we're trying to make predictions. For example, if we're trying to predict the daily new cases, we would have to use very noisy data to make predictions to predict the new number of cases per each day. And other benefit of using probabilistic machine learning would be that you would be able to find a distribution instead of a point estimate. So if we were to study the effects of social distancing, for example, we would be able to make a better prediction and create a distribution of how social distancing versus no social distancing, what are the effects of these things when the data that we're observing is very noisy and has a lot of uncertainty. And the last advantage would be precisely the capability of representing and computing with uncertainty. So this, an example would be autonomous driving application, where you could use these Bayesian principles in deep learning to produce these heat maps that highlight the uncertain areas within the vision system. And by using this information and these highlighted areas with a lot of uncertainty, you can make better judgment and decisions that would be more safe for the drivers in the vehicle. So one could easily imagine that the application for these algorithms would be possibly in biomedical field or robotics, autonomous driving, and finance, and more. However, the problem that we have seen when we started researching these probabilistic machine learning algorithms is that the CPUs and GPUs are inefficient for Bayesian inference. And what we're trying to solve is this specific problem of existing computing platforms not being efficient for this particular algorithm. So today I'm going to talk about PGMA, which stands for Probabilistic Graphical Models Accelerator. It's our first silicon accelerator for Bayesian inference. We designed it using algorithm hardware co-design for parallel Markov chain Monte Carlo inference. And the goal of this talk is to demonstrate an efficient mobile implementation of Bayesian inference accelerator. And we do this, we demonstrate this by using 4 unsupervised perceptual tasks as an example of how we can accelerate these tasks using our accelerator. These tasking are stereo matching, image restoration, image segmentation, and sound source separation. PGMA was actually built as one of the accelerators in our SoC for machine learning research, which we call SM5. We use TSMC 16 nanometer process, and it's 5mm by 5mm SoC. PGMA consists of 2.3mm by 1.3mm within this SoC. And we designed this from RTL to tape out in 3 months between 2 postdocs and 3 PhDs using what we call ChipKit, which is an open source framework that we released for agile research test chip development. So it includes things that you could use for fast design and testing. And we've open sourced it on GitHub. So if you're interested, please let me know. And these are some of the chips that we have designed over the years. SM2 and SM3 are Arm M-class SoCs that we built for machine learning. And we have SM4, which was actually presented at Hot Chips 2 years ago by my colleague, Paul Waltmore, which was our first A-class SoC for machine learning. And then this SM5 is where the PGMA was included. And we also are currently testing SM6, and we're about to tape out on an SM7 in about a month. So these chips all resulted in the aforementioned the ChipKit, which is our agile research test chip framework. And SM5 uses dual core Cortex-A55, and which is connected to PGMA by NIC 400, that is 128 bits wide, which again goes through the 32-bit AHB to connect to PGMA. And I'm going to get into more specific details about the architecture of PGMA in the following slides. But before we get into the actual microarchitecture, I would like to first talk about the models that are supported, the inference algorithm that we use, and the applications that could be ran on this PGMA. The model in particular that we have focused on is called Markov random field, which is a generalization over Ising model, which is graphical models as shown on the right. But our PGMA could also run various other models, including hidden Markov models and regression and more. The inference algorithm that we have used is called Gibbs sampling, which is a Markov chain Monte Carlo algorithm, which is derived from statistical physics. And the applications include computer vision and audio processing algorithms, such as the one that I mentioned earlier. But we could also run run combinatorial optimization problems, computational biology algorithms, recommender systems, topping modelings, and more. And I'm going to use the image restoration task as an example to show how we could map an application to our accelerator. Left is the input image that is destroyed, and the right is the restored image. And what we do is that we create a Markov random field, which is shown on the right, and we map the input pixels to each of the variables that are shown on the right. So each pixel would correspond to a variable, and what we're trying to find is the variables that are on the bottom that is represented as blue nodes through the unsupervised training process, where the result would be the reconstructed image. And so the blue nodes are representing the values of the reconstructed image as a variable, and the edges between the nodes are representing the encoding the relationship between each of these variables. I'll get into more details about this, but if we were to look at the diagram on the left, which showcases the sampling procedure. Gibbs sampling on MRF, what you do is that you visit every single node in the graph and you sample a new label for that specific node iteratively. And when we look at the diagram, the blue node is the node that is currently being sampled. And you can see that it is looking at all the edges that are connected to this node. So you can see that the observed node, which is colored green, there is some sort of a relationship between the two that is represented by the edge. And then you're also looking at 4 edges that are connecting the specific node to its neighbors. So using these 5 edges, we're computing the new sample for that specific node. And then once we're done, we're visiting the next node and then the node after that. And then we repeat this process until we sample every single node in an image. And we iteratively go through all of the nodes again until we reach convergence. So you could easily see that it is a very iterative algorithm, but it is also very, very hard to accelerate this algorithm because each sampling procedure depends on the previous state, which means that in this inner for loop, each iteration depends on the previous loop, which makes parallel programming really hard. So we have used algorithmic hardware code design, hardware code design to tackle this problem. But before we get into how we solve this problem, we're going to first focus on what is within the loop, the line number 4, which is the actual sampling procedure. And this is our Gibbs sampler, what we call, this is the market architecture for the Gibbs sampler. You could easily see that even the sampling process itself is a sequence of long sequence of operations. You could, so this specific Gibbs sampler supports up to 64 states and labels per node. We use 32-bit variable fixed point arithmetic, and we included a pseudo-random number generator in each of the Gibbs samplers, and we use an iterative architecture to minimize the area. So using this Gibbs sampler as a building block, we're going to implement parallel Gibbs sampling. Going to explain now how we did that by leveraging 2 levels of parallelism. So if you look at the left pseudocode, you see 2 for loops. And for each of them, what we do is that if you look at the outer loop, we perform what we call an asynchronous Gibbs sampling. What we do is we sample different tiles. So we divide the image up into different tiles, and we sample each of the tiles as if they are separate images. So this breaks the sequential nature of the Gibbs sampling, which is why it is often called the asynchronous Gibbs sampling or hog-wild Gibbs sampling. And then once we take all these tiles, if we look at within the tile, what we do is we perform what we call a chromatic Gibbs sampling, where we're sampling conditionally independent nodes concurrently by performing graph coloring on the graph, and we're sampling all of the red nodes shown in this graph concurrently, and then in the next iteration we'll be sampling the dark blue nodes, and we repeat this process until convergence within the tile. And then in their outer loop, what we do is that we basically go through all the tiles, and then we perform multiple iterations of that until convergence as well. So this is the actual PGMA architecture. You can see that there's a global graph cache that's in the middle. Our PGMA supports up to 640 by 480 images for these vision tasks. And we have 2 subgraph tiles, which means that we're able to process 2 tiles at a time. Each of the tiles can be as large as 4 by 640. And each of the tiles contain 4 Gibbs samplers. And how this works is that if we are processing a specific tile, what we do is we copy the information from the global graph cache into the local graph cache, and we basically also pull in the input information into the buffer, and then we perform the chromatic Gibbs sampling within the tile to process that specific tile, and then we synchronize the information to the global graph cache, and then we just repeat this until we process all the tiles and until we reach a convergence. The number of Gibbs samplers and number of subgraph tiles were determined as an optimal for our given chip real estate within the SoC. And I'm going to talk about how we could actually expand this and add more Gibbs samplers or add more subgraph tiles later for different problems and for different implementations. This slide is showing our results for the unsupervised perceptual tasks that I mentioned earlier: image restoration, zero matching, image segmentation, and sound source separation. So I just wanted to note again here that these results are not, these results do not use any kind of labeled data set, and they're both training and performing inference on the fly, which means it's completely unsupervised. This slide is showing our multi-threaded server class CPU results, where we initially tried to find out how well this algorithm scales on a server class CPU. We use Intel Xeon to run chromatic Gibbs sampling for stereo matching application. We could see that, like, as you increase the number of threads, the amount of speed up actually plateaus, and we're not able to get anything above 6x speed up. We also compared the result of our PGMA with off-the-shelf embedded platforms such as NVIDIA Jetson TX2, which is a GPU platform, and Xilinx Zynq ZCU102, which is FPGA SoC platform. Compared to TX2, we were able to achieve 48x throughput improvement per watt. And compared to Zynq, we were able to achieve 247 throughput improvement per watt. And these were both optimal implementation of chromatic Gibbs sampling. Furthermore, we also compared our results with the A53 on the same SoC. And we also compared our results against the embedded FPGA in SM4, which was the same A53-based ML SoC that we had built. You can see that the PGMA achieves up to 1380x throughput improvements over ARM A53. And if we actually look at the throughput per watt, the improvement increases up to almost 2000x. And if we actually include the area as well, the throughput per watt per millimeter squared is over 4000x. One thing to note here is that both A53 and embedded FPGA are more than twice the size of PGMA. And to summarize all these results, if you look at this graph on the right, figure on the right, PGMA could achieve nearly 2000x throughput per watt improvement over A53. And even compared to the embedded FPGA, we're able to achieve significant speed up. And as I mentioned, our PGMA was configured for our specific chip real estate and also the application we have decided to showcase the 4 unsupervised perceptual tasks. And in order to scale PGMA, what we could do is we could scale within the subgraph tile, where we could add number of Gibbs samplers for a linear increase in throughput. And furthermore, we could actually increase this, we could actually parallelize by scaling with more subgraph tiles. And this would also increase throughput linearly as well. And with that, I would like to summarize this talk. We have presented our first silicon Bayesian inference accelerator, which we call PGMA. It is capable of running various probabilistic models, including Markov random field, hidden Markov models, regression, and more for applications that include computer vision, audio processing, recommender system, topic modeling, combinatorial optimizations, and more. And we've used a very scalable architecture. We've used algorithmic hardware code design to enable parallelism in a very natively sequential algorithm. And it uses hierarchical architecture, which allows us to nullify and alleviate some of the problems that could arise from implementation side of this accelerator. And we have showcased an energy efficient mobile implementation for real-time unsupervised perceptual tasks. And as I mentioned, the same architecture could actually be used for other applications that are not mobile applications, but are cloud scale applications. So we're currently working on a server class version for cloud applications. So if you're interested in this, please find me after this talk. And I'd like to mention that this chip design was done really in a very short amount of time using ChipKit, which is our open source framework that allows us to iterate between different designs really rapidly and also allows us to test chips really fast as well. And with that, I would like to conclude my talk. I would like to thank my contributors, my colleagues, Yuji Chai, Marco Donato, Paul Watmore, Thierry Tambe, Rob Rutenbar, David Brooks, and Guyan Wee. I would like to also thank my sponsors, DARPA Craft and DSSOC programs, SRC Jump, Ada Center, Intel, and ARM. Thank you for your attention.
Hi, thanks Glenn for the great talk. There was a few questions that came up. I guess one question a lot of people are interested in was, could you share more information about why CPU and GPU are so inefficient for Bayesian ML, given that actually a lot of people are using GPUs and CPUs now to do their Bayesian training?
Great question. So CPUs and GPUs are not necessarily that great for Bayesian inference for several reasons. First of all is the fact that, as I mentioned in the presentation, the fact that it is a sequential algorithm by nature, and oftentimes these sampling procedures, the sampling operation itself has a lot of sequential operations even to perform one operation of sampling, which results in a lot of cycles just to obtain one sample. And also the other reason could be that there's also intermediate information that needs to be stored within the sampling procedure that may necessarily be larger than the memory element close to the compute unit, which results in low memory efficiency, in particular for GPUs. And also lastly, random numbers. CPUs and GPUs generally have, generating random numbers is also a sequence of long operations, whereas we're using pseudorandom number generators in hardware, which allows us to efficiently generate them close to the actual consumption compute logics. So I think those are the reasons that I can mention as one of the reasons why having hardware accelerators for these Bayesian inference accelerator would be more preferable for over CPUs and GPUs.
Okay, another question on the technology was, your charts show voltage scaling down to 0.4 volts. Do you scale the on-chip memories as well down to the same voltage? If so, what error mitigation mechanisms do you use?
Could you repeat the question one more time, please?
Yeah, this was from Karthik Swanithaman. Your charts show voltage scaling down to 0.4 volts. Did you scale the on-chip memories as well to the same voltage? And if so, what error mitigation mechanisms did you use?
Yes, so we actually scaled the on-chip memories down to the same voltage as well. And we didn't use any specific error mitigation mechanism. So it could very well be that the errors could have resulted from the actual SRAMs as well. But one of the advantages of using MCMC-based inference method is the fact that it is an iterative algorithm that depends on the random numbers, which means that oftentimes these errors that might occur oftentimes doesn't actually really affect the end result, which is one of the advantages of using this particular algorithm. So we didn't discuss this in detail today, but there are actually a lot of opportunities when it comes to scaling down the number of bits. For example, we didn't aggressively scale it down for this particular implementation, and we didn't address it, but we're doing a lot of research on how we could bring down the number of bits used for these compute logic that are used for the sampling process.
Okay, thanks. So this question wasn't actually from me. It was from Yaya today at Intel, but and a few other people asked, how come you're not using RISC-V?
Well, great question. One of my collaborators, Paul Watmore, he's actually at Arm Research. So for us, it's basically working. We decided to work with Arm processors. I am actually interested in also RISC-V potentially for future implementations as well.
So on the algorithm, there was a few questions. Can the Bayesian accelerator be used for supervised learning as well?
Yes, I mean, I would say that the Bayesian inference accelerator shines the most when you're using it for semi-supervised learning or unsupervised learning. But yes, you could use it for supervised learning as well. It's just that when you get into the realm of doing supervised learning, we all know that deep learning works really well for supervised learning applications. So then you know the efficiency of how well the Bayesian inference accelerator works versus like the existing deep learning accelerator becomes of a question. So I think you could still use it, but in terms of the efficiency, then you may not want to potentially use it over other existing accelerator if you already have the other accelerators on chip, for example. Like our SM5 also had CNN accelerator and RNN accelerator on chip. So depending on the application, you may want to actually use these accelerator over the Bayesian inference accelerator for unsupervised learning.
Okay, maybe just one final question. This is from Kevin Krull. Any plans to commercialize the technology?
Yeah, so I mentioned briefly on the in the presentation, we have been working on the next version of this hardware as at Stochastic, which I'm working as a CEO. So we are working towards commercializing this technology. We're currently working on our first product. So if you're interested, feel free to email me. I should be able to discuss this in more detail offline.
Okay, great, thanks. I think it's a great talk and a great way to end the session.